Okay, let's get started with creating a repository for the main project, and then create the HAL repository. I'll go to my GitHub account. I'll create a repository for the main project. If you already know how to create these, just skip this part and go to the next lesson. So I'm going to be using GitHub. Main course in the projects material. Folder. Okay, now I have a project in my computer that I can just do git control, version control over it. So now it's time to go and create a HAL library. I'm going to create the HAL library example for ESP32, but it's gonna stay exactly the same for different processors. So I'm going to create a repository. GitHub is 32. Okay, where should be placed? It will be the main course in the root of the folder, and we call it HAL. Okay, now, so we also have a repository for our HAL library. I'm going to start with the Blink example and build my code on top of that. So what I do is that I go to the Blink example, I'll copy my files, get started as a starting point, and come and paste it in the newly created repository. If I go back to the repository that I created, I would see that a lot of files are added, and I can push these changes to my repository. Obviously, pushing it directly to main is not a good strategy. You have to create a develop branch. So let me do that right now. And work on your develop branch, and let's see. Make the description as much as you can, make it more clear, but for the sake of time, I'm just gonna put a very brief explanation. So one of the things is that you created a new folder inside this project that will act as a submodule. I'm going to create a develop branch here too, so I wouldn't be directly working on that branch, on the main branch, and I have to protect both these branches from direct push. But again, you will know how to do your git control. Okay, now let's go and open the folder that we just included in the repository. So I'm gonna go there, main course and main course. This is the main project folder. So now we have that billing example. And we have to go and build the project because we cannot copy the components in the ESP32, the managed components. It has to be downloaded and initialized on the first build. So we're going to give it some time and come back once the build is finished. Okay, now the build finished, and we know that our project is working and ready to start development. So, as you can see, we created this folder. I added something in the README file, and let's go back and see what's happening. So, I have some changes in my HAL library. Updated README. I'm gonna push that, and this commit will be used in our main project. Again, use a very good description for your comments. I'm just using very simple ones. Now I know that the commit in my HAL is used here and tagged to the same commit. So this will act as a submodule in my project, and I can manage the main project and the HAL library as a separate code. Now let's go and create our first module. We are going to be replacing the blink example. So I'm going to start with creating a HAL module for GPIO. First thing before creating your first module is to define a template for yourself. So I already created my templates. There are different ways to include templates in your project. Some IDEs like the IDEs that are Eclipse based, they allow you to define different templates for different programming languages. Like you can define a default C template or default C header file, a default C++ header or source file, and when you are creating new module based on the tags that you are putting it in the template creation, it will pick up the name of the module, replace all the parts in their code, and it would be really easy. But the simplest way would be create a folder, create a header and source file, and use these as your templates, and just manually replace them. That's the easiest way. That also sticks to your project. So if you are moving project between different team members, the template stays the same. So I usually create two sets of templates. One, a simple one, a simple module, like HAL GPIO is a simple module. We initialize it or we deinitialize it, and that's it. But there are some modules that need, if you're using an RTOS, they need a background task. So I also create a template for that. And the difference in these templates for me is that the simple templates have initialization and deinitialization, and the task templates have a start and stop function. So by looking at those functions, I will know that this module has a background task, the other module doesn't. Again, these are the things that you have to define it the way that you're more comfortable with, but I'm going to go with this simple one and start creating my first HAL module. Okay, so I'm going to copy the simple, paste it in my HAL library, rename it to HAL GPIO because I want to create GPIO. I have to go and rename my files, rename this to HAL GPIO. That would be the name of my module. And let's rename this to HAL GPIO for the source. So now I have a header and a source for my GPIO. Let's see what else I need to do. So I need to replace my default template name, preserve the casing with HAL GPIO, update the dates, the information, your copyright license, and so on. And you will see that in my templates, I have these sections in the header file. First the includes, then the macros, the global and public constants, and the data types, and it already comes with the default data type for that module. This is the module name, that would be the HAL GPIO, and the underscore T would define that this is the type def for this module. I will include all the inputs that are needed to handle in this module in this structure. The next part is the public functions, and the portal of the public functions. By default in my template I have init and the init. So in the initialization I will initialize the GPIO. In the deinitialization I will fill up any allocated resources. And it's really important to, this is equivalent to constructor and destructors in this C++ language, and it's really important that we call the dinit once we are done with this module. In a lot of firmware development, once you define a HAL library, you don't need to release it, but we will get some examples that we have to call the dinit and fill up the resources. For example, if a pin is output in my board design, it will stay output for almost forever. We never have a functionality that would need to change the direction of the pin midway. If it's output, it's probably going to stay output. So we don't need to call dinit and call another initialization on that pin. That's why a lot of these will stay the same. But even though, as a practice, even if we are not exiting a loop, we will add the initialization after the loop to make sure that if for any reason the infinite loop, if it breaks and we have an exit condition, we make sure that the resources are freed up. So next, before I start implementing my new functions, I also have my own return status that I will show you later on. It's part of my HAL library, and it will define different codes as my own internal status that will translate the normal codes to my own. So almost all my functions will return this status, even though if in some cases at the moment I don't know any specific return status, and it's equivalent to void, I try to avoid creating void functions in case in future a new status is added. So in case my function always passes and returns okay, I just return okay, and not to worry about that. And this will give me an opportunity if in the future or in different processors, in different MCUs, if the conditions are different and I need to return a specific error code, I would have the capability. So you probably never see me creating a function that is void. I always return a status. This rarely happens to be a void function. You can see that the init and init function accepts the type definition that we defined here, and this kind of declaration will be followed across all the modules. So always the first argument would be our configuration structure. So another function that I need to create for my GPIO is a set function, right? You remember from our code standard that all the input arguments of a function starts with the T, and if it's pointer, it's going to have the P prefix in there. And what else do I need when I want to set a pin? So I need to know if it's a high or low, right? So can I use an integer and do that, or what is the better way? So the better way that we will always do is to define enums. All our enums will start with the module name. So in this case, it's HAL GPIO, and pin state, right? So I'm going to start with low, set it to 0. I'm going to have high, and I'm going to have state max. So I always do that, and I always have a max in my enum. So you will know that this value is already set to 2, and I can use this max to check if my arguments are within the range and are valid. So if it's invalid, I'm going to return an error. The name of this would be pin state, and you can see the name of the module is included in all the types, and my enum follows the same name of the type definition, and only have different states added in the end. So I'm going to use this newly defined type as an argument and create a state. So obviously you have to define your documentation here. I'm not going to bore you with that, so you know what to add here. You use Doxygen documentation and explain what this function does. So we created these prototypes. Let me copy this, go to the source file. We have this, replace this. Okay, and in our source file, what are the sections? We have include, we have macro sections, we have data type sections. So these data types are private and the user will not see it. Whatever we put here is private. The user will not see it. The user only see what's in the header file. So any constants here, we define them. If we have any static private variables, they are defined in this section. Any static function prototypes are declared here. All the public functions are here. So you can see the init and the dinit. I newly added a new function. So I'm going to add it here. And as a default content, I'm going to put this here. So I have the placeholders for my initialization, my deinitialization, and just setting the pin. What do I need to know for defining a GPIO pin? So when you are defining the type def or the configuration structure of the module, you need to think in a wider mindset. You need to think about different MCUs and create a superset of the variables that will support all different scenarios in future. Don't worry if you miss something. So adding things to these functions should be easy. Removing things would be really hard because it could make other HAL libraries invalid. So we will add as much as we can. So let's think about what is needed for a GPIO. The first thing we need to know in some of the MCUs are if they are having I needed to include the std include. So when you are including standard libraries, use these. When you are using internal and your own, you have to use the double quotes. This way you can distinguish if it's a standard library of you or your own. So let's say int 8. The first thing we would probably need to know the port number, right? Does ESP32 have the port number? Doesn't, but we have to think about the wider picture. Some of the MCUs do, and I'm defining that as an int. Maybe I can pass -1 for the ones that don't need that to be able to check if I need to, but you can make it uint. So the next one would be the pin number. Which pin number we wanna configure and define. What else? I needed to do. This should be the last object structure that we define in this section. What else do we need to be able to define a GPIO? Pause this part of the video, think what is needed to define a GPIO and see if you are seeing the same thing. So you already thought about this and you probably think, yeah, so I need to know if the pin is input or output. So how do we define that? The best way is to create a type definition enum that will define this. So it would be HAL GPIO pin direction, right? Pin direction. So this would be a definition in direction input, right? Or HAL output, and again I'm gonna have a max value to be able to range check my inputs, right? So I'm gonna have a pin direction, what else do I need? If my pin direction is input, maybe I can define an interrupt callback. If my chip does support pull up and pull downs, I need to have an enum for defining inputs, the pull ups and pull downs, and a lot of other things that you could think of. So think as wide as you can. I'm going to skip this and fill out all the fields that I think is necessary for the GPIO, and come back to you in a moment. Okay, so I spent some time on the library and added some parts that I'm going to go through and explain what and why I added these parts. So we have the direction mode that would show if the pin is input or output. We have an enum to show if the pin supports should support an internal pull up, pull down, or be floating. We have different types of outputs. Some chips support the open drain outputs. It might not be supported with every chip, but as I mentioned previously, because this is something that has to be covering all different cases, we have to include it. If our current chip doesn't support that, it should return an error when we try to use that in the new chip. We have interrupt, so a lot of almost every processor supports interrupt on the GPIO pin. The interrupt could be on the rising edge, on the falling edge, on any change. Some of the chips support a specific low level or high level. We have to include it in our enum types. We have a callback for interrupt. So if we define a GPIO input as an interrupt on a rising or falling edge, or any change, we can define a callback to pass the data. And finally, we have the HAL GPIO configuration structure. We have port number, we have pin number, we have a pin mode. I'm gonna call it pin, direction mode, pull mode, and output mode, depending on what state you want to define that GPIO pin. We can use this to define it. We have a specific part for the input interrupt. Again, you have to sit down, think what you need, and maybe after a while you come back and see, no, you need to add new things in your template. So just include as much as you can think of, but don't worry if in future you need some new thing, you can come and complete it. So over time, after a while, your templates would be covering everything, and after some modification, you don't need to touch it ever. There is a special field that I add in my configurations. The type is void pointer. It's a pointer. I start that with underscore. So in my naming convention, no variable is allowed to start with underscore. Only this field is allowed, and this is equivalent of having a private variable, private member in a class in C++. So because we don't have that, I include a void pointer, and in my source code I will show you how I will reuse that to store any specific data that I want it to be carried with my configuration structure. So for example, if we don't know how many GPIO pins the current chip will support. So a chip could have more, another chip could have less. Either we have to create static arrays in the source file to be able to keep all the pins. That would be a waste of memory. Or we can create a placeholder like this void pointer and allocate dynamic memory at the initialization, which we have to be very careful about it, and I'll explain how we handle that. So we allocate the memory and in the initialization, and we release it on the deinitialization. So anything specific to identify that pin, whatever is necessary, we're going to store it here in this field. And the user, because it's the void pointer, user will not know how to use it. So it's completely hidden from the user, but we can store whatever we want. So we have the init function, we have write or set the pin, read the pin, and that's all we need from this function. So let's go to the C file. In the C file, we include whatever header file is necessary. We don't care if these are processor or MCU specific. This is the only place that we are allowed to include any header files related to our MCU. If we have any global variables, we declare it here. If we have private static functions, we declare them here, and we get to the init function. So all the functions in our modules will have the configuration structure as their first input argument. Let's make these const. I forgot to do that. I did it here. All right, so we might check some of the inputs before processing it. The first one would be, is it even a valid GPIO pin number? Does this processor even support that? If it doesn't, we return an error. We change that to pin in the header file, so I have to update it here. So we go and check what needs to be done in the datasheet of the MCU, how we can configure that pin depending on the parameters that are set in our configuration structure. We either define that pin as an input, as an output. We add a callback for interrupts and so on. We configure it. You need to go through the MCU datasheet or documentation to be to know what to do here. And the next section would be the deinitialization. We figure up and release any resources allocated in this specific module. We didn't need to store anything in this field, but we have to keep it. Maybe another MCU needs something to be like a handler or something. I will show that in other examples what that field could be used. So although this specific HAL GPIO didn't need this, still we have to keep it for another MCUs. Maybe they need it. So as part of our my standard and my template, I always keep this field in my configuration structure. So in the initialization, we release any allocated resources. I renamed the pins to set and get. So again, you have to go and check the data sheet and the documentation to see how to read the pin or how to set the state of a pin. So now that everything is ready, we can go and replace the Blink example with our new HAL library. Another thing that I'm going to do is to replace the Boolean with a new enum. So I would have a little more control over it. So I defined a new enum to define the state and set the pin low or high. I'm going to use that for my public functions. Then I want to set the pin instead of the boolean. I will use my enum type. And I'm going to go here and replace this. So because this is not a boolean anymore, this. This should be this. No boolean. No boolean. I can't think of anything that isn't binary when it comes to the GPIO pin, but just to be sure, it's better to have a type rather than a binary value. So another thing is instead of this, I will have to check if it's high. So we put the constant on the left side. So if I make a mistake, instead of double equals, I put one equal, it will break the build as part of our coding standard. All right, so now we have a library for the HAL, and now it's time to go and rewrite our main file. Okay, so you remember our first example, the Blink example. I renamed the file to main just to make it more general. And you remember that it was looking like this. So I want to do the same. I have to remove everything because I don't want to include any processor or MCU specific header files. I want to use my own, right? So because it's my own library, we put it in the double quotation, and I already configured the project CMake file to know look in the under the HAL folder and find these headers. So I just include that here. So we have that GPIO pin. We know GPIO pin number 2. We want to use. We still need this. I'm going to make it G to be compatible with my own standard. I don't need these. Okay. Okay. This. So we have two functions. The first one is to configuring the pin, and another one I'm gonna also include my login, HAL login. So I included a log module. Again, login could be completely depending on the processor. Different processor might have different methods of reporting the log messages. This one is using just a serial port, but could be different on different MCUs. That's why I'm putting it under the HAL folder. And I'm going to start replacing this. So it would be log debug something, right? So We want to configure our own pin. How do we do that? Remember that we have the HAL GPIO type. So we have, because we want to access this later on in here, we want to make it a global. So we make it a static HAL GPIO type LED. Sorry, we underscore LED HAL GPIO. Right? I'm going to initialize it with all the fields with 0. So here I'm going to use this variable and define the parts that I need. One of them is I don't want interrupt on this one, so just disable it. The pin number is this macro. So we just use that. Another thing is port number. Sorry, I just noticed that this wasn't very good. I'm going to replace that later on, but this was the pin number, right? So I already defined the pin number, the port number. What else? In the pin field, what do we have? Direction mode. So what direction mode we want? How GPIO, or the name of the module, and it's direction mode output. We also had something like output mode. So how GPIO output mode push pull. So I'm going to use that. What else? We don't have any pull up, pull down, so we should be fine. This should be the configuration that we need. So we defined we set all the parameters that we needed. Again, this is not a good idea to put everything in main, and this is not a good idea to hard code these values. I will show you later on what should be the code structure and how it should be. We just want to check our HAL library here. So I will define something here, return status type rs, and I will set it to OK. By default, we always initialize our variables. So the next thing we want to do is to log debug. Let me reuse that previous one. LED and print a string and return a status string rs. So I can translate the return code or my return status and get a string for it to be able to print it, and it would be easier to see what happened in my functions. So what do I need to do? I need to pass that structure. It will initialize it, and it will print if it was successful to initialize it or not. So when this function is called, my port is configured, and I can set the level, right? So I have to replace this, but how? Again, I like to check my return values. So I create variables here, variable to show my return status. Then we want to set the the value, right? So again, HAL starting with the name of the module, and we set it the set name. We have to pass our configuration parameter, and the next one would be SLED. Sorry, GLED state. And we remove the old one, but we also want to see something in our terminal. So we print a message set in and return state with string rs. Be able to see that in the terminal. Okay, so at the start of the main function, it will configure the LED through our own structure. We have an infinite loop. So I'm going to replace this with my own log message called the link. We change the state. And we need to have a delay. So that means we need a delay function in our HAL library to be able to support this. So we need to go and add that. We cannot include a FreeRTOS related function because we might be switching to another processor and it might not support the FreeRTOS. So it's better to bury the RTOS part in the HAL library, and when you are switching between platform, you will know if it's supported in the new platform, or you need to use a new port of that RTOS to be able to use that. So it's better to unify that and bury it in the HAL library. Okay, now I added some parts for my OS. One of them would be OST, OS. Again, I'm initializing my stats v 0 as a default value, and how OS delay, let's go T, how delay. These are the two parameters that I need. Yeah, so these are done. The last is to replace this with our newly created delay function. It will be how OS delay, the second delay as a configuration structure, and the last argument is false. So in my delay functions, I have a binary as a last argument that shows if the delay in the loop should be compensated. This means if I set this to the length of executing this part of the code would be deducted from the delay. So if you want to run a loop in a timely manner that if the period is fixed, you set that to true, and it will take care of it. I mentioned that even though that this loop doesn't have any exit, as a best practice, I always call my dinit functions when I don't need my modules. And this is really important to get used to it because I've seen a lot of issues that I forgot to include the deinitialization, and later on there was a condition. I added a condition in my while loop that was exiting the while loop. Obviously not this one, but if you have multiple tasks in your project and one of them is exiting, and if you forgot to call the dinit function, it will lead you in the memory leaking issue because you're allocating some memory in the initialization, and when you do that it will cause if that happens in the loop and each time you initialize and allocate memory and you don't release that memory, then you are consuming the RAM and you are not freeing it up, and that will cause a lot of issue for you. So let's see. All right, so what's the issue here? Let me have a look and fix that. Okay, I renamed the files and I updated the includes. I also initialized my log messages and are printing the log module. And now we are ready to flash our evaluation board again. Let's build it and flash it. Building now. Flashing and now opening the port, and you can see printing the messages. One is the OS initialize, delay initialize, configuration link was okay, so everything returned okay, and we know that setting the pin is working fine, and you can see the blue LED is blinking in this example. So now we have a HAL library to set the GPIO pin. None of these functions are MCU related, so we can easily port this example to another MCU without needing to change anything here, right? So we only replace whatever is in the HAL folder. So I added a couple of modules. So we just replace these files and our main application layer will stay the same. Obviously, this is bad practice. We come back to this in the later on in the course, and how and what should be in the main file. Basically, main file should be empty, just calling our application and running it. But for the sake of having an example, I'll put everything here, and you can see no MCU specific header files are included. In none of these, any header file that are MCU specific are included, so user will not see anything that is directly related to the MCU, and they will not be able to by mistake using anything that is MCU specific. So you have to make sure to hide everything in your source files in the HAL library, so the user wouldn't have any visibility over it and wouldn't be able to use it by mistake. Once they use your own HAL library, any of your team member or yourself when you are using your own HAL library, you are making your code portable. That's the end of it for our example to use the HAL for GPIO.